Welcome to calculus. I say welcome and I say congratulations. Calculus is a course that people talk about with these kind of tones where it's just sort of up there and it's almost unreachable and it gives folks nightmares. And I'm not going to say this is going to be an easy course, but I say welcome. You guys have made it. I think, and it's hard to get statistics on this, only about 15% of Americans take a calculus class, either in high school or in college. So you guys have made it to the top, and I hope that we have a great semester together. There are a lot of handouts that I've given you, but the one that I want to start with is the real big one. And at the top it says Cliff Notes version of Calc 1. So this page is just here as kind of on one piece of paper. We're going to try to make sense of all these symbols by the time the semester is through. It's okay if none of them make any sense at this point. We're going to skip to the next page, and we're going to try this jet fuel problem. So can you guys introduce yourselves to your table mates and work through everything on this page? So for the most part, what kind of a graph did you guys draw for number 2? What's a line? A linear graph, assuming that every hour you use exactly the same amount of fuel. And that's a reasonable assumption in the beginning of the problem. And in fact, Peter, the person who was the math teacher that actually was on the plane and had this problem to solve, solved it exactly in the way that you guys did number 1 and didn't win the prize because it wasn't linear. It's going to be something that maybe looks a little bit more like, let's tell this thing to go away. Maybe something like that. Because as time passes, what happens to the weight of the plane? It's going to get smaller, which means that the amount of fuel you need to use to move the plane also becomes less and less. And so something that's increasing, but increasing slower and slower and slower. And saying it's increasing more and more slowly isn't very precise. So let's start to talk a little bit more precisely about this rate of increase. What I want to do is take a look at these 2 points, the drag point and the C point. Drag has nothing to do with the plane and the air drag. It's just telling me that that's the point that I need to drag. So what I want to do is recognize that these 2 points horizontally are always going to be the same distance apart. That's how I built this thing. So whatever distance they are horizontally here, it's the same horizontal distance here. It's the same horizontal distance there. And it might be kind of hard to believe unless you're looking for it, because these points look really far away here, but they look really close here. And it's because the vertical distance is not the same. And that's exactly what we mean when we say that it's increasing, but more and more slowly. So what I'm going to do is draw a secant line. And if I were to take a line and draw it through those 2 points, what is that 7.52 representing? That's the slope of the line. And so what it means is, on average, for this beginning part of the trip, we were using 7.52 thousand gallons per hour. No, I didn't give you any specific numbers. You couldn't draw anything precise, but for this thing that I've made up, it's that. And as we move to the right, what happens to that slope? It's decreasing. And so, okay, sure, the graph is still going up, but now it's only going up by about 1.5 every step to the right. And if I went further to the right, it would go up by even less. Okay, so let's come back to here. We'll go to the next page and start with number 1. Joe, could you read number 1? Okay, so the syllabus looks like this. I put a bunch of copies on the table, so make sure you have one. If you don't have one, let me know. And let me also reference the 2 other documents that you should have, a total of 4 things in your hand. Should be the big packet, should be the syllabus, it looks like that. There should be something that says project number 1 on it. It's got a triangle on the front top. And then finally, the pre-calc practice problems or sample problems, something like that. Does everybody have 4 documents? What don't we have? Anybody else need something? You need a syllabus? You're good. There you go. Okay, so we're not going to read through this whole thing together, just some real quick highlights. There's my information. My name is Ian. My office is around the corner. The fact that my home number is on the syllabus means it is okay to call me at home. Studio and office hours are here. I'm just going to mention the studio. The Math Studio is a wonderful resource we have at GCC. Take advantage of it. It's a big old room. It happens to be right across the hallway here, where oftentimes you'll find a math faculty member available to answer your homework questions or study questions or project questions or any questions. Questions about life. You just go right over there. All the problems are solved in that room. I will hand out a schedule for when it is covered real soon, but it is on this green piece of paper right here, okay? Officially, our class starts at 8:40 every day, and officially that is the only time that you need to be here. Shoot for 8:35. But unofficially, there's an 8 to 8:35 time block, which I know that nobody has class. It's built into this schedule, so you guys have time to be over in the studio right across the hall, get your homework questions answered right before class, help with the last minute studying and projects and all that. Anybody have anything to add about the studio? People that have been here in semesters past? Super, go ahead. Yeah, yes. Sometimes there's pizza. Oh, good point. The textbook happens to be in the bookshelves all the time, so you can use it in that room whenever you're here. And answer keys too.
And calculators.
Right, lots of calculators there as well.
And if you want to play with like Wolfram Mathematica,
Thank you. Okay, super. So take advantage of it. All right, the textbook is there. I will never ask you to bring the textbook to class. Some of you might want to bring it to class. It's up to you. You can read the description and the course goals. We'll move on to the next page. And there's a list of resources. One of the things you're going to do tonight is log into Moodle. Just make sure you have access to our course. You'll see some materials up there. YouTube we'll talk about on Friday, but there's a link there that you can check out. And then down here, it's lots of stuff that you get graded on. You can read all of it. It's overwhelming in the beginning, but it'll make more sense when we have specifics in front of us. What I do want to talk about is the way that I grade you. At the end of the semester, I'm going to give you guys a numerical grade, which gets converted to a letter, A, B, C, D, with pluses and minuses. And you're actually going to tell me how you want me to grade you. I have 3 different options here. If you think you do really, really awesome on tests, and you don't have to do a lick of homework, and we all hate you, those of you that I'm talking to, then you can choose the test heavy one. And then there's no points assigned for homework or even showing up. If you don't tend to test well, but you're a workhorse outside of class, and you're going to put that time in doing the homework and the projects and all that, go with the test light option. If you're somewhere in the middle, there's standard. And then if 3 choices isn't enough, you can actually make up your own, as long as you pick numbers that are in the ranges that I have assigned here. Now, I'm not going to ask you to make this choice until the class after I hand you back the first test. So you're going to have a sense of what all of those things mean and what your semester looks like and what your study habits are going to turn out to be this semester. You will have a lot of information before I ask you to make a choice, okay? So let me take a look at the calendar, which I think is on the last page. So you can see here at the moment, test number 1 is scheduled for September the 28th. I will grade it. I will hand it back to you on October the 1st. On October the 3rd, you're going to tell me what percentages you would like me to use when I calculate your course grade. Okay? So you have a long time to think about this. You'll know what all of those things represent before I ask you to commit to something. Any questions at this stage about that? Okay, so this calendar is something that I'm going to project at the start of every class to give us a sense of where we are and where we're headed. You'll note that the dates are there. The classes are also numbered. This is class number 1. In the packet, you will see references to class number 1. That's this one. The reason I like the numbering is that if there's a snow day, then the dates change, but the numbers are consistent, right? So just keep looking at this calendar, and you'll have a sense of where we are and what's going on. If there's a snow day, I will reprint this page with the right dates, all right? We have quizzes. First one is coming up on September the 14th. We have projects assigned. First one is going to be assigned on the 10th, but I happen to have given it to you already. You don't have to look at it until the 10th. It is collected on 17th of September. Any questions on this page? Okay. Then let's come back here to the big packet. And we'll start on number 2. Could you read number 2 for us?
system. How do you change it? How do as a result of this increased reading,
Mhm.
the area of the circle also change radius area calculus will allow us to quickly.
Okay, thank you. Number 3.
Let's start by watching a clip of
Oh.
it.
Number 3 for.
Let's start by watching it.
Can you keep reading?
Fiscal from February 2010.
This number, this 2,000 degrees per second, is in a very real sense an instantaneous rate of change. It's really, really fine-tuning, looking frame by frame. What was happening at that one moment in time? And as it says here in part C, we're going to be looking quite a bit at instantaneous rates of change. They are at the heart of this class of Calc 1, and we're going to be talking about them throughout the course. Okay, let's try number 4. Can we go to the next table? And Chris?
The problem with the Ron Lake. The temperature of the water in the lake is down.
Okay. It gets colder, right? We've all experienced this. Colder water is down there at our feet. There were times when I would swim and I would just kind of try to keep my legs up real high because I didn't want my tootsies to get cold. All right, so we agree the cold water is down at the bottom. So where's the coldest water? Like probably really at the bottom, right? Okay, so if it gets colder as you go down, then the coldest water is at the bottom. That makes sense. Let's go to Andy for C. The top of the lake freezes first. Is it? The bottom freezes and then it floats up. That's what Todd has witnessed. Is that true? What have you guys seen? All right, well, you're jumping to my punchline, so let's step back there. So from my experience, I see lakes freezing from the shore, from the banks first at the top, and then it kind of closes in, and then I imagine at that point it starts to freeze down. And so we kind of have to get some idea of how these two things seem contradictory. The coldest water is at the bottom. That's what it says from swimming in the lake. But witnessing lakes freeze, they freeze from the top. Okay, let's go to part D. Yeah, go ahead. Okay, you don't need to read the equation, but there's the equation that tells you what the volume is as a function of the temperature. It turns out that water doesn't have a constant volume. How much space a given amount of water, 1 kilogram of water, how much space it takes up depends on the temperature of the water. And so here's the equation. So if you happen to have a graphing calculator handy, then let's get it out. And can you guys graph this equation? What you're going to do is try to find a good window to find that graph. If you don't have a graphing calculator, look on with somebody, but I encourage you to bring a graphing calculator to class every day. We will be making frequent use of them. Okay, so let's see if we can work on finding a good window together. First of all, what should the x's be? They were actually given in the problem. Kyle? Yeah, this formula, as was read to us, only works between 0 degrees Celsius and 30 degrees Celsius. So it doesn't make sense to look outside of that, that interval. Kyle used the word range, and from an English standpoint, that makes sense. From a math standpoint, is range the word for the x's? It's the domain, right? Okay, so the domain is 0 to 30. That's great. All right, and then let's see. So which one of these says look up real high at 1,000? Is the Y max. All right, so let's go down and we'll change the Y max. All right, I'll make it 1,100. I don't know what I'm looking for yet, but at least 1,100. Should we change the Y min or leave it at -10? Okay, so we're not going to have negative volume. So, I mean, oops. So, at the very least, shouldn't be any less than 0. Okay, so I'm going to go between 900 and 1100, and we're going to see this graph. Well, that was exciting, wasn't it? It looked like it was going to be a straight line, and then all of a sudden, 1 pixel higher. All right, do you feel like this captures the behavior of this function? I mean, this does not leave me feeling very good about that function. Like, it looks like it's just a horizontal line. And you can kind of play around. So what if we try to like fine tune? I don't know, maybe we'll go like 950 to 1050. And then we'll take a look. Maybe that'll kind of pull it apart a little bit. Change the last one to what? Change the Ymax to 1000. Okay, let's. I'll change this one to 999. Okay, so this is a really, really tight window, right? 999 to 1000. If I didn't know Todd, I would say we're probably going to see nothing because we're only looking at this little horizontal sliver. But Todd generally knows what he's talking about. So let's take a look. All right, so I see something, and I see something that I would not have at all guessed from the other graphs that we saw. It just looked horizontal with a tiny, tiny like increase at the end. I did not see that at all. Okay, so let's come back to this, and we'll say well done to Todd. But to come up with that 999 to 1000, like that's really asking a lot. I feel like it would take me a long time to trial and error, figure out, oh, this is really, really tight, 999 to 1000. Let's keep going here. F. Can we start with this gentleman?
Seemingly unrelated exercise. Solve for 0 degrees to 30 degrees. You may, and you should, use your calculator to solve. Don't use the graphing calculator on this part of the question. Store your answer on your calculator.
Okay, so it's hard to maybe figure out what kind of an equation that is, but the variable is t, and I see some t squareds, and I see some t's, and I see something without any t's. What's the name of that kind of an equation? That's a quadratic equation, t squared. Okay, there are a lot of ways to solve quadratic equations, but if it's ugly, what are you going to do? You're going to use a quadratic formula. So give it a shot. Use the quadratic formula on this thing, and we're going to store the answer as z for 0. So Wolfram Alpha is just this computational tool that you can pretty much type in any math thing and it will solve it for you. So I just typed in, I'll make it a little bit bigger in case you can't see that in the back. I just typed in solve and then I typed the equation. That's one of my favorite things about Wolfram Alpha is that you don't have to memorize syntax. Pretty much it will figure out what you, like if you have half a brain in terms of typing in something, it will figure out what you mean. And so there's my equation. It found me 2 answers. 79 is not inside of our domain, right? We said 0 to 30 degrees. So we toss that one out and we get this 3.96651. There's the graph of the 2 answers. And there they are on the number line. So, okay, 3.96651. Let's go with that. So if you happen to have that number on the calculator, here's how we store it, 3.96651. I said I wanted to store this number as z. How do I get to the green z on my calculator? I hit the alpha key. So we go alpha and then z. And anytime I ask the calculator to tell me what z is, it will say that until I give it a different number for z. And so then if we come back to this packet here, I asked you to fill in the table. So even if you didn't quite get the 3.99, what was it, 3.966 or 996? 3.966. So even if we didn't get that, still we can just put in 3.96651. Is that it? Okay. And then we're going to fill in the rest of the table. And the goal here is not to kill ourselves typing in that the volume formula over and over again. Do you guys know a real easy way to get the calculator to give us those numbers, given that we've already typed in the y equals? Is table. So table is a really, really nice feature. We'll just take a quick look at it. If you go into, first I'm going to go into table set, which is this yellow button right above window. And I'm going to make a change here. I'm going to scroll down to the independent, and I'm going to change it to ask. So just highlight the word ask and hit enter. Doesn't matter what the top two numbers say for this. And what that's going to do is allow me to type in these particular values of t as opposed to a list, like 10 degrees, 20 degrees, 30 degrees, some orderly list. I want these. So then if I go into table, which is again the second button, and then right above graph, it should give me a blank table. And this is where I tell it what x is. So what I'm interested in is these x's. 0. Okay, I don't feel like typing that again. What could I put? If I tell it z, it knows. Z. Alpha, z. And then 30. Okay, now I'm starting to get a sense of why Todd's window was so good. He said 999 to 1,000. Well, that's just about what this thing is, right? 999. So which one of these is the smallest number? Is the Z one, is the 999.74, but how much smaller is it than the previous number? It's like a tenth. It's hardly anything like, compared to the number 1,000, they're basically the same, but it is a tiny bit smaller, and that's why we saw that little kind of downward loop when Todd gave us the window. And then how big is it at 30? It's only up at 1,004. Really doesn't move much at all. So what I'm going to do is move on to the next page. And we'll get our next reader, Toby. No, sorry. Yes. Okay, thank you. So we're going to create a tight window. And here's what that means. We're going into window. Do we like the X's? Yeah, so that's still the domain of this function. But now when it comes time to put in the Y's, what should I put for the Y min? I want it to be really tight at the bottom. Is that Z value? It was, what was it? It was 999.74. Let's put that, 999.74. And then what was the biggest number in the table? 1003.8. Was there another digit or was it just 8? Okay. So if you've got the calculator and you've got that window typed in, hit graph. And this is what I mean when I say a tight window. The graph bottoms out on the screen and it maxes out at the top right corner, right? This is everything we wanted to see. And you can see that bottom isn't very much. It's not very significant. It doesn't go much lower than at 0, but it does go a tiny bit lower. And Ernie, in fact, you kind of knew the punchline. What did you say about water? Water is most dense at 4 degrees. Is this something you guys knew? A few people kind of heard this before. So why do we care about that? Well, first let's fill in some of this stuff. So we had a graph, and the graph, I guess, looked like it was here, and then something like that. And the points that we had were this guy. What was this one? This was at 0 and 999 point. Which one was the first one? 87. Okay, so that's that one. And then the bottom one here. I guess I shouldn't have drawn that horizontal. It's not the x-axis there. That's just the bottom of our window. And what were the coordinates of this guy? This was the 0.966. And then what was the temperature? The volume was. Okay, so we've got that point. And then one more point at the top right. What was the temperature there? That was the 30 degrees. And the volume was 1003.8. So I feel like we know everything there is to know about this graph. It goes down just a tiny bit, bottoms out at about 4 degrees Celsius, and then the volume increases as the temperature increases. Now, that point that we came up with was sort of a miracle. I just gave you like this random quadratic equation and I said solve it, and somehow that gave us this answer. Soon enough, we'll figure out where that quadratic equation came from. But what's going on here? Let's see, what temperature has the least volume? It's this temperature, about 4 degrees. And so if you imagine having, 1 kilogram of water, and it has the smallest volume possible, then what's true about how dense that water is? It's going to be the most dense, right? If you have some stuff and it's compressed as much as it possibly could be, but it's still 1 kilogram, then it's going to be really dense if you have to compress it down. So the answer to this, what has the greatest density? It's the same, 4-degree water. So why is that important? Well, let's see. Suppose it's really, really cold in the lake and we're not going to swim in the lake. It's so cold. And let's say that the water gets down to, I don't know. So we've got our lake here, and this is a side view of the lake. We've got water up here at the top. And we know that the water down here is the 4-degree water. That's the most dense water, so it sinks to the bottom. And so then up above, maybe it's 5 degrees, and then the water at the top is still very chilly at 6 degrees. But the water at the top gets cold because it's cold outside, it's winter, and at some point, all of the water in this lake is going to be a certain temperature. You know what temperature that is? It will kind of approach the ambient temperature outside. Let's assume it's really, really cold outside. What temperature will all of the water in the lake become before it gets to 0? It's going to get to 4. It's going to all be 4-degree water, because the 4-degree water, like the water at the top is the water that's exposed to the cold, but the 4-degree water is kind of hiding down at the bottom, and they're protected down there by warmer water at the top. So the only way to access that 4-degree water is to make everything 4 degrees, so the 4-degree water doesn't have anywhere to hide, right? It's never going to be at the top to get colder because of the weather until it's all 4 degrees. So at some point, the whole thing is 4 degrees. And then what happens to the water at the top? Remember, it's still really cold outside, much colder than 4 degrees outside. It's going to get colder. It's not going to freeze instantly from 4 degrees, but if the water at the top gets colder, then maybe the water at the top is 3. What's below? 4. 4 is going to do its darndest to get down at the bottom. And okay, so now some of that 3-degree water is touching the 4-degree water. So some of the 4-degree water is going to still get a little bit colder. And so maybe we've got the lake a little bit down the road, and maybe the 4-degree water is kind of smushed down, and then we've got some 3, and then some 2 is really cold at the top. And you can see maybe we'll get these kind of layers of water, and ultimately you'll get something like this, where it's 0 at the top, and then 1, and then 2, and then 3, and then a little pocket of 4-degree water at the bottom, and then what happens at the top? And it starts to freeze. And as it freezes, what's it going to do to the 1-degree water that's right below it? It's going to start making it colder. And so this stuff at the top will start becoming more and more 0. So maybe you got like this thick chunk of ice at the top. But at the bottom, you still have some 1s and some 2s and some 3s and some holdout 4s. And no matter what happens, the 4s just kind of keep getting pushed down there at the bottom. And if it's cold enough outside and there's not that much water in the lake, it will all freeze. I'm not saying we can't make ice cubes, right? You can. You have had ice cubes in your drink. So it is possible to make everything freeze. But that 4-degree water being the most dense is what allows life to exist at the bottom of the lakes. So it makes it so that the fish don't end up like kind of being frozen from the bottom up to the top. And plant life and animal life get to live at the bottom of lakes and oceans because of this. Because that tiny, tiny dip, it seems so insignificant. It seemed like a horizontal line, actually, when we first graphed it. But this is how life exists at the bottom of the lakes. It's because of that 4-degree water. It's just a tiny bit more dense, and that's all that we needed. Okay, let's go to number 5, and I think we're back around to Toby. Can you read that definition again, please? Okay, so we'll see that phrase a bunch, critical point. Go ahead, Toby. Okay, so you guys know y equals x squared. What's it called? It's a parabola. And Bottoms out right there at the origin. And so according to our new word, what is that guy called? That's critical point. Because it's flat, it turns, right? It was going down and then it was flat for just an instant, just a moment, and then it went back up. So that's a critical point right there. Now, given, I was hoping that more folks would have calculators here, but given that we don't, maybe we're going to skip this one because it does involve a lot of graphing stuff. So you can have a look at it later. It's actually something you can just do independently outside of class. Just follow the directions, see if you can work your way through. I don't know that we'll come back to this one necessarily, but we are going to skip it just because of the calculator thing right now. Okay, so on the next page is a problem here at number 6. But before we do number 6, I want to take another look at the syllabus calendar. You don't need to pull this out at this moment, but I just want to point out that if you look at the sections that we cover, this column right here, 1.1, that's today. Next class, we're jumping to 2.1, then we're back at 1.8. 2, and 2, 3, then we're back in chapter 1, some 2s, some 3s, some 1. The sections that we're covering, the order that we're covering them is not the order that the textbook follows. And this is a change for me. I've taught this course a couple of times here at GCC, and in the past, I have covered the sections in the order that they appear in the book. And so what that does is chapter 1 is a review of pre-calc. And it's like, I don't know, 2.5 weeks or so of just doing review stuff. And then we start calculus proper. And I think it's better this way. I think it's better to talk about something called a derivative next class. I think it's better for a number of reasons, but suffice it to say that the order is going to be out of order compared to the textbook. And so I don't want you to feel like this is kind of random jumping around. There was a lot of thought that went into this shuffling over the summer. And I also want to say that because there were so many changes made to the materials for this course over the summer, I know that there are going to be some errors someplace. I did my best to find and change everything that should change, but there's going to be some homework assignments where I give you the wrong page, or there's a problem that we haven't covered yet, or something. So I ask you to bear with me this semester. It's the first time I'm doing it in this order. I think it's going to be a lot better for you, but you guys are kind of the guinea pigs in terms of the materials. So bear with me. All right, so we're on number 6, and this young lady here. That makes sense? It's not something we think about, but right now blood is pumping through all of your blood vessels, and it takes energy to push that blood through, and there's energy that's lost because of friction. Okay, can we go back to Sam for A? Okay, so what I'd like you guys to do is chat with your neighbors and answer that question along with B and C.